Oh, good morning. So in a minute, I'll take any questions you got on the homework today. We have the homework quiz today, and then we've got a little bit of new notes. Your e-learning assignment, it's going to be very short. I may have a very short thing. I haven't decided yet. There may be a very short thing, but the main assignment is what's already on your syllabus, right? And I'll be available on Zoom, and I'll put hours on Zoom if you've got questions on the syllabus. But that's really going to be the main thing. I'm trying to decide. I may have one of the a 2-question or a 3-question multiple choice thing, just to kind of get the concepts in your mind. But I may not. I'll let you know. But it won't be too much in addition to what is already there. A reminder about project start on April 7th. So here's my my recommendation on this. The reason I wanted to start on April 7th instead of April 5th is because I really didn't want you to be doing a presentation the day you got back, because I would like you to be able to have a spring break. So what I'd like you to do is, there's no enforcement on this, but I would like you to have your project done before you go on a spring break, and then Monday evening after spring break you can go through and practice or whatever you need to do, run through it for yourself one more time or whatever. But my goal would be that you didn't have to do any working on the project over break. But if you just started on the Monday after break, that's a lot. So I wouldn't do that. Yeah. No, okay, yeah. So no, it's not memorized. I don't care what there is no point on the grade book. There's no point in the rubric on delivery, right? What I would like is to be able to ask you questions, and it's kind of clear that I'm not expecting you to be the expert, but that you know enough that you can have a conversation, and that it's not just you're parroting something that you read but don't really understand it, right? But there's nothing on the rubric about delivery, and I also don't have I envision this. Remember, it's going to be presented in small groups. Remember, we're doing multiple at a time, and you're presenting to 3 or 4 people at a time, and then we're going to rotate through all of them. So, if anything, I would it's more of a presentation than a conversation. But it's not the goal is not, this isn't a public speaking project, I guess is what I'm trying to get at. So when I say practice, what I mean is, the thing says it's 5 to 7 minutes, right? Refresh yourself on what you're going to say, make sure you know what you're going to say, make sure that you're 5 to 7 minutes. But I don't need anything, I don't need memorized, I don't need you to worry about saying or anything like that, right? I just want you to have an idea what we're talking about. Any other project questions? All right, so again, that starts April 7th. So like I said, the 8.4 and 8.5.6 should be done by the end of the e-learning day. That's the idea on the syllabus. And 8.7, you can have finished by Monday. If you want to do test corrections from the last test, those should be done by Friday this week. All right. What questions on the homework tonight? Go ahead, Emma. 41. 41. All right. Dad pushes tangentially on a small hand-driven merry-go-round and is able to accelerate from rest to 15 RPM in 10 seconds. Assume that the merry-go-round is a uniform disk of radius 2.5 and has a mass of that. Okay, so the mass of this thing's a disk, and we have a mass of the disk is let's say 560. And I got one kid sitting here, one kid sitting there. So the mass of each kid is 25. The radius is, sorry, you can't see what I'm writing. The radius is 2.5. Looking for torque and force. What else do I know? What would you call that RPM, Emma? What symbol? Yeah. I'm starting from rest, so I'll say omega naught is 0. Time is 10 seconds. All right. So, big picture, right? Where we're trying to get to is force and torque. And if we have torque, we can get to force pretty easily, right? To get to torque, I need two things. I need iota and I need alpha. So if I can find these two, then I can get to torque. If I can find torque, then I can get to force. That's fair. So let's talk about how to find each of these. So alpha, how could I find alpha? Anybody got an idea? Go ahead, Malachi. Yeah. So this will be, we'll get this, right? And in essence, you can say that alpha is delta omega over delta t, right? So you'll know I went from 0 to this, right? I get alpha that way. Iota is just a little bit more complicated because what happens is this is a combination, the way you want to think about it is this is a combination of the extended object, which is the disk, plus two particles. So you can think of each kid as a particle, right? So the iota, the total iota of the whole thing is the iota of the disk plus, there's two kids, so plus two of the iotas of the kids, right? And we're going to treat, so the disk, if you look at your equation sheet, right, is 1/2 mass of disk r squared. We're going to treat each kid like a particle. So a particle is just mr squared, right? Mass of this would be mass of the kid, r squared, right? And then from there, you know that torque equals iota alpha. And from there, you know that force equals, torque equals r force. Okay, good. Any other questions about this? Different one, Grace?
Yeah. Reading 4014.
Mm-hmm. Okay. For the sake of making sense out of it, let me at least talk through A first. Okay, so we've got a constant angular velocity of 1.6 revolutions per second, which is an annoying unit. Really, what I need to do is I need to get that into radians per second. I don't know how I'm going to do it this time. We haven't really done this conversion, but what do you do to it? This one's just going to be multiplying by 2 pi, right? Because it's not RPM, it's revolution per second. It's an annoying unit, but okay. So let me just get this to radians per second real quick. So that's something like 10.05 radians per second. Okay, the friction, so the friction's a force, is 1.5 newtons. And part A says, how large is our torque if the diameter is 9 centimeters, which means that the radius is 4.5 centimeters or 0.045 meters. Okay, so I assume you did torque equals RF and got that one. When you get? Okay. Now, if I want to know how long it takes it to stop, what we're going to say is that now this is my omega naught, right? Omega, if it stops, is going to be 0, right? And it's telling us what the iota is. Sorry, kilogram meter squared. So what I want to do is alpha equals delta omega over delta t. And then once I know alpha, torque equals iota alpha. You'll have found alpha here, torque is there. Iota is, sorry, oh, I see. I got to go backwards. Sorry, torque and iota. So you plug in this to get alpha, and then you plug alpha in here to get time. That works. What else? All right. Okay. I want to start with notes because then we'll do the quiz, and then anytime after the quiz you can use for the syllabus. So if you recall, in this unit, what we're doing is we are recasting all of physics in terms of rotation. So just a reminder of where we're at, right? The first thing we did was we talked about kinematics. That was also the first thing we talked about this year, right? So the first thing we talked about this year was acceleration, position, velocity, right? The first thing we talked about this unit was theta, which is angular position, omega, which is angular velocity, alpha, which is angular acceleration, right? Then we went from kinematics to dynamics. So translationally, that was when we were doing Newton's laws, we were doing forces, masses, and acceleration, right? And for rotational, we talked about this in terms of torque and iota and alpha, right? The next unit we covered translationally was circular motion. For obvious reasons, we don't need to redo that, right? Because we're basically doing all circles. So we're not going to redo circular motion for this unit. We're doing it all the time. The next unit we did was at the end of this semester, which was energy. So we need to talk about how do you deal with energy when you deal with things that are rotating. So I'm going to sort of keep following the same pattern that we've been following, right? Concept, linear translational, rotational angular, comments, and we're going to start with the idea of kinetic energy,
which we know as Ke equals 1/2 mv squared. And I'm going to call this KET for translational kinetic energy. So it turns out things that are moving, right? When we talk about things that are, this is particularly true about things that are rolling, right? Things that are rolling do have this translational kinetic energy because their center of mass is translating. But they're also spinning, right? And the fact that they're spinning or rotating means that it takes energy to do that, right? So it turns out that when you've got something, it actually takes more energy to make something roll than it does to make something spin. So let me just write down an equation, and then we're going to talk about it some more. I'll bet we can predict what the equation is. So we're going to call this KER for rotational kinetic energy. I'll bet you can guess the equation if you think about it. If you use all of the parallels we've talked about so far, does anyone want to try and guess what 1/2 mv squared becomes when it becomes rotational? Go ahead, Malachi.
1/2 m.
You were talking about W, right?
Yeah.
Omega squared. So that part's right, but it's not m. Yeah, it's iota, right? Because that's translational inertia, right? This is rotational inertia. What this means is that it actually takes more energy to roll than it does to slide, or even a lot of times, if you think about a car. So let me grab something. I have two things here that are, they're different sizes. It would be nicer if I had things that were close to the same size. I want to say something about these two things as they roll down, right? If I roll this cart and this ball down, what you're going to see is that the cart rolls faster than the ball, right? The reason the cart rolls faster than the ball, I mean, are you convinced by that? I'll show you again to make sure you see that, right? You can definitely see that the cart is accelerating faster than the ball. Okay? Now here's the deal. Most of the cart, yes, the cart has wheels, but if we're talking about most of the mass of the cart, most of the mass is not on the wheels. Most of the mass of the cart is on the cart, right? That means that primarily, we'll just ignore the wheels for a second. This is only translating. Yes, the wheels are rotating, but they're small. But this thing is primarily translating. A ball has to translate and rotate, right? And since it has to translate and rotate, it needs more energy to do that, right? So this is the idea of where rotational kinetic energy comes from. You have to have enough energy both to make something translate as it moves and to make something rotate. I'm going to talk about one other thing, and we're going to do calculations with this. This other thing we aren't really going to do many calculations with. I don't think there might be one question on the homework about this, but I think it's important to see nonetheless. And that is the concept of work, which, if you recall, is force parallel times distance. Hi there. Welcome back. So taking a look at this, if we, this would be the translational work. If I were to talk about the rotational work, anyone want to guess what it is? Instead of force, it would be what?
torque, instead of distance, it would be not arc length, because arc length is still translational, just translational in a circle. Theta, right? Or we're going to say delta theta. So this is the same sort of idea, right? If you want to make something rotate, right? So if you imagine, so you know those, like, on the pirate cartoons where you have to, like, turn the wheel to make to make the sails move up the mast, you know, kind of, right? How do you do that, right? You've got people on the end of these handles and you're pushing them, right? What are you doing? You're applying a force at a radius. So you're putting torque on this wheel, and by putting torque on this wheel, you're doing work on the wheel, right? So these are the ideas. Now I want to be clear about something. Unlike everything else we've talked about, these units are the same. Kinetic energy is kinetic energy. Whether it's rotating or translating, it's still kinetic energy. So it's still going to be measured in joules, right? Work, whether it's force times distance or torque times theta, you can actually show that the units come out the same. So energy, there is no such, like rotational energy is not a different thing. It's still joules. Yeah.
So, like, is that why you're really specific about being a Newton meter, no, a meter instead of a Newton meter? Because radians don't have a meter.
Exactly. Yeah, that's what. Yeah, we said that torque is a. So if you look at it, yeah, torque is a meter Newton times the theta. And then we can rewrite it as a Newton meter, which is a joule. But yes, but I wanted the reason we call it a meter Newton and not a Newton meter is because even though it's the same unit, it means something totally different. You can't just say that torque is an energy until you multiply it by a radius. All right. So let's try an example. This is what was in the energy unit. This was one of the simplest problems you could have, and it still is a pretty simple problem. But we just have to be careful the first time we do it. So we're going to imagine here we've got a ramp. And we're going to take it, we're going to say this is a sphere, right? So we're going to take a sphere of, I've already worked this out once, so let me use the same numbers so that we can check our work as we go along. So let's say that this sphere has a mass of 1.8 kilograms and a radius of 0.2 meters. And then let's say that this ramp is 5 meters tall, and we want to know how fast, and I'm talking about in meters per second, is it going at the bottom. So this is like a marble or something, right? All right, I want to give you a second to see if you can see what you can do to start this. So talk to your partner here for a minute and see what you can do to start this. How about here in a moment, we're going to have some time today.
fourth round. Four rounds.
And then.
Okay, so yeah, maybe we'll do the, like the multiple here today, and then we can do the, paper. Like, do you usually drive? All right, anyone got an idea here? Go ahead, Tim. Okay, so we could start by finding it. Yeah, I'm going to, because of a point I want to make in a second, you're welcome to find it, like to get this, but because of a point that I want to make in a second, I'm going to leave it algebraic for a second. But yes, you could find it from that, right? Because it's a sphere, so it's 2/5. That's from the equation. Yes. All right, so that's something we could do. Again, we could get a number. I don't want to get a number right now because I want to make a point with it at the end. Go ahead. Yes. So this is a conservation of energy problem. And yes, at the top, what I've got is I've got potential energy, right? I'm going to assume this thing's frictionless, so no work. What do I have at the end, though? It's different than usual. It is kinetic energy, but there's two types, right? Because I'm rotating and I'm translating. So when I do this, and I think, did I put potential energy on the equation sheet? I don't remember if I did. Okay, good. So if you don't remember, it's mg(y)0 is going to equal, rotational is going to be 1/2 iota omega squared plus 1/2 mv squared. Now, this was where I wanted to, instead of like getting a number for this, I wanted to plug it in. So if I do that, if I plug this in, I can do 1/2 times 2/5 mr squared. Sorry, that's not mr squared. So that's what I'm plugging in for iota. I'm going to plug in something for omega in a second. Anyone know what I can plug in for omega? Because the problem is it's annoying to have to find V and omega separately, right? It's annoying that we've got two different things that we can find. Can we relate these in any way? How? Go ahead, Malachi. Yeah. So if we take this equation and we rearrange it, we can get that omega equals V over R. So I can plug that in there, right? And then also, just to make this look a little bit different, instead of putting the squared here, I'll just square these two. And you can see now maybe why I didn't want to calculate this earlier, right? The reason why I didn't want to calculate this earlier is because we now have the convenience of being able to say, oh, we don't need to worry about radius anymore. The r squareds cancel out, right? So then this becomes mg(y)0 equals 1/2 times 2/5, which is 1/5 mv squared plus 1/2 mv squared. Masses can also cancel out. And I can take 1/2 plus 1/5. Anyone want to dust off their fraction addition skills and tell me 1/2 plus 1/5 is? 7/10, right? 2/10 plus 5/10 is 7/10. B squared is equal to gy0. And so the final speed
is going to be what? Square root of 10 g y naught over 7.
Now, the reason why I don't always like make us do this algebraically, but the reason why I want to do it algebraically this time is it's really interesting. There are two things that do not matter for our answer, right? What does not matter for our answer? Mass or radius, right? What does that mean? That should mean that if I get two solid spheres of different sizes, I think I gave all my marbles. Oh, here. Yes, right? That means if I take two solid spheres of different sizes, right, and they can even be different masses, it should not, so the speed that they go down the ramp shouldn't matter, right? So if I roll these two down, we should find they roll at the same speed. So both mass and radius have no bearing on how quickly they go. All right, let's go ahead and finish it off just by getting a number here. Is that right? So that's how you do the math on this. But again, like I want to say, I want to make clear from this, the interesting points that sort of transcend this problem are that mass and radius don't matter. What does matter, though? There is something that does matter. What?
Why?
Say again.
Why?
Oh, fair enough. How high it is. Okay, that's true. That's true. Yes. I thought you meant y, w, yeah. It could be how high it is, but let's say that it's the same ramp, right? If it's the same ramp, we're now saying that I can get objects of any size. Hey there. I just want to get out here with the feet here.
I have my eye drops on.
Oh, cool. Do you want to leave it? Well, here. Yeah, you just leave it there for now. I'll give you that for now, and I'll talk to Translational Work and finish this. Last page is bonus. The last two problems are bonus. So what this is saying that I can take any two spheres, right, and I can roll them down, and they can be any size, they can be any mass, as long as they're solid spheres, and they'll go the same speed, right? But what won't go the same speed? So these two are about, close to the same radius, right? But does our math say that these two things will go the same speed? No, it does not. Where would that? What would change for this? Yeah. The iota would change, right? And instead of 2/5, it would be in this case 1/2, right? So the only thing, so we're going to say that mass and radius don't matter for how fast I'm going. But one thing that does matter is I'm going to say the geometry of the object does matter.
with that in mind, we're going to make a prediction. So I've got a sphere and I've got a hoop, right? You can look on your plate and see what's the difference for the iota for a hoop versus iota of a sphere. Tell your partner which you think is going to make it down the hill faster. All right. Let me grab my cards here. Nathan, which do you think will make it to the bottom first? Tell me what. So it's mass and radius, yes, but what makes a sphere different than a hoop? Ainsley, what do you think? So which do you think is going to hit first? The sphere, why? Right, yeah, that's the key. Oh, that's what you were saying, Mark. I see now. I see. Because you mean it's not too big. I see. I'm sorry, I misunderstood what you were saying. Yeah, that is correct, right? I was actually thinking this was 1/2, but I was wrong. So yeah, 1 is bigger than 2/5, right? So if 1 is bigger than 2/5, right? This thing is going to be harder to rotate, right? The idea is it's harder to rotate because it's 1 is bigger than 2/5, right? So if this is harder to rotate, then we should see that the solid sphere goes faster than hoop. So a solid sphere goes faster than hoop because 1 is bigger than 2/5. All right, with that in mind, tell your partner hoop or solid disc, which is going to win. Tell your partner what you think. All right, Val, who wins? Say again. The disc, why? You can look at the fraction for the disc. 1/2 versus 1, right? 1/2 versus 1. 1/2 is less than 1, so 1/2 is easier to rotate than 1 is. So again, the disc should go faster than the hoop, right? But I could take 3 different hoops, right? And since only geometry matters, mass and radius don't matter, I should be able to take 3 different hoops. And if I really release them at the same time, it shouldn't matter how big it is, right? All right, any questions about that? Okay, like I said, this gives you enough information now to do everything up through section 8.7 in the syllabus. So what I'm going to do here in a moment is I'm going to hand out the homework quiz. Then when you're finished with the homework quiz, you can work on the syllabus.